Jeff?
Thank you.
With the one Windows machine here.
Yes, and just to answer that question as well, we use concurrent hash map a lot, but we try and use it as little as possible because, again, it's too easy to fall into this trap. If I have a concurrent container, I don't have to worry about multi-threading anymore. You still do, because if you can do your algorithm without the concurrent container, you're going to be better off than relying on these magical containers to hide that complexity from you. So I'm here to talk about the next section, the first of these sort of case examples of where in visual effects industry people have tried to multi-thread and what we found in the process. In my case, I'm Jeff Lait. At Side Effects Software, I've been for a very long time now, and I've seen a few attempts of us multi-threading on different boxes, and so I'd like to share what has happened over those attempts. So our main package that we're probably best known for is Houdini. This is a visual effects package. It's well known for its procedural approach to modeling and geometry manipulation. It has a lot of solvers and simulations in it as well. We also have a render, which I'll jump forward to, called Mantra, and it's a microvoxel and also a ray-traced rendering system. And there's something which ties those two things together, which is our Vex programming language. We first wrote this language as a shading language. It was, inspired by the RenderMan shading language to provide the SIMD operation. So the reason for SIMD back in these days wasn't for parallelism. It was to hide the cost of the interpreter. So if you operated on 1,000 shading samples at once, you didn't have to worry about the interpreter overhead. It would sort of disappear. But we found very quickly, as SSE and MMX showed up, that we could trivially vectorize all those operations, and as multi-threading showed up, we could trivially multi-thread them all. And this meant that because we did not just use it for shaders, we extended this language to the rest of our package. We use it for deformations, we use it for simulations, we use it for procedurals. All these things just became multi-threaded when we used Vex. So when we wanted to multi-thread Houdini, the first question becomes, why are we multi-threading at all? And if you look at Python, there's this horrible global interpreter lock, which I think other people might also talk about, which basically stops it from having any form of multi-threading. You can have multiple threads, but unless you're just doing blocking on I/O, you're not going to get more than one thing operating at once because it keeps having to lock on this interpreter lock. And the Python community often responds saying, this isn't a real problem. What you should do is just run separate Python processes, and then those will be able to use all your cores successfully. And this is sort of a distributed computing rather than multi-threaded computing. And when I think of distributed computing, I usually think of high-performance computing with these really complicated, OpenMPI type systems. But we should remember we're all distributing already. When we have a render farm, that is effectively a distributed computer. And the distribution mechanism can be very simple. Just assign some computer, look on disk for this RIB file or this IFD, render it, and then store it in this location. And so one reason why I can't just trivially distribute is if I was to run 4 copies of Houdini, well, I have large enough monitors, I can have 4 copies visually there at a time, but I really only still have 1 mouse. So it's very hard for me as an artist to make all these copies of Houdini run at full speed. And so you still want to be able to get that individual copy faster somehow. The other big reason to avoid jumping into distribution is we're guilty of a very common programming problem. As programmers, we really love to see a hard problem and say, this problem's too hard for me to do. I'll solve a harder problem. And for example, game development, I want to have a story for my video game, and writing a story is hard. So I'll write a procedural system to write a story for me. Then I don't have to write a story. Well, writing a procedural system to make an interesting story is harder than writing a story. If you can't write the story in the first place, you're going to have trouble making that meta level. So similarly, if you can trivially distribute a problem, such as rendering frames on a farm, you should be able to equivalently trivially multi-thread it. And so if you're not able to multi-thread it because it's too difficult, you're probably going to run into troubles with distributions. In particular, the problem you run into is shared caches, because when you just trivially distribute something, each of those separate processes will recompute all of the caches you need to understand your scene. So if you're doing a renderer, they all have to load copies of the geometry, so you have multiple copies of the same geometry in memory. They all want to build a KD tree for doing ray traversals. They'll redo that work and store the extra memory for it. So what you'd want to do in their distributed renderer is share those cache structures between them. But this becomes a very difficult problem to organize over the network and decide what structures are shared and when you synchronize them. And if we think about the computer hardware we have on the CPU with its buses and L1, 2, 3, 4 caches. That is a hardware-accelerated cache sharing mechanism that we should take advantage of. And that's what you're doing when you're multi-threading. You're not getting rid of, you're not actually having a flat memory model, because we never really have a flat memory model, but you're having hardware acceleration to give you the illusion of a flat memory model. All this said, distribution is a useful approach to take because it really forces you to get your data to be local. And so, like if I do a fluid simulation like this and I distribute it between 4 machines, and each machine only sees a slice of those particles, the advantage is when I do an operation, like I want to add forces to all the particles in my slice, I'm only working on a quarter of the data set, so I'm going to fit better in whatever cache tier I have on my system. And so you end up seeing this strange effect where if I distribute on the same machine, I'll get better performance because I force my algorithm to be very data local. Of course, this sort of insight can always be brought back to the multi-threaded case. It just comes to the forefront when you distribute. So with Houdini, what were the challenges we faced when we decided to start multi-threading it? The first and primary challenge is Houdini is a very old program. It was originally released in 1996, but the code survives back from Prisms before it. That goes back to the Omnibus days, which is a very, very long time ago for code. And by comparison, the Core Duo was released in 2007. And this is a bit later than the inflection point that James showed because we're a bit slower on the uptake to realize that the clock rates stopped going. We kept asking them, is this a dream? Is this a dream? And eventually, we stopped pinching ourselves and realized we had to deal with multi-threading. And so what we did around there is I think about the time the quad-core Duo came out, we said, okay, developers, you don't get the fastest computers anymore because the fastest computers were, single-core, high clock rate machines. We said, we're going to cut the clock rate down and give you a quad-core machine. So you start thinking about how do I get it fast with many, many CPUs rather than just a single CPU. And it happened to be at this point we'd already multi-threaded a lot of our code because there were multi-core machines before that. We were on the alpha. I remember having a 4-socket alpha. There was, of course, the SGI origins. There were these big, giant pieces of hardware that you'd dream about. But all that code we had written just completely failed to scale when we started to work with these quad-core machines. And it was largely because of the problems that were going to show up later. The other problem we have with Houdini is we have a node graph that describes how the operation should perform. And we, the programmers, aren't the ones creating this node graph. It's artists building this node graph. And the way they build the node graph is not with a very directed requirements analysis approach to designing their node graph. It's a very much an iterative, constructive process. They're jumping around, looking at different parts of it, cooking different parts of it that trigger evaluations from any particular place. And they build a very big spider web of dependencies very quickly between all the nodes. And this isn't an exceptional thing we get from a few artists. It seems to be a very common behavior we get back. And my theory of it is when you build a procedural system, you're basically building a programming language. You actually are programming. But the artists don't want to program in the very clean room, elegant sense that might appeal to a programmer. They want to program the way they paint, where they can paint over things with more and more paint. So you find them painting over their program with more and more additional nodes, which undo the effect of the earlier nodes. But in some ways, those earlier nodes still peek through and result in creating some texture to the resultant program that isn't there if you try and build something too clean and straight. So it builds very beautiful programs. They're very different than the way I'd program. But I don't think we should say that the way they do it is wrong. So we want to very much support that behavior. And to do that, we have to compute the dependencies at runtime. So here we're trying to cook the node at the bottom, and as it goes up the tree of wires, it comes across a switch node, and the switch node will pick one of its 2 inputs to compute next. This would not be a problem, except we don't know which input to compute until we evaluate the parameter on that switch node. The parameter on that switch node might itself require other nodes to be computed. So we can't just build a task diagram of how to compute this tree without bouncing back to the computation world and switching between dependency computation and evaluation. As we'll see in the later presentations, this is very disastrous for trying to do task-based parallelism. So faced with these problems, we had to decide how we're going to multi-thread Houdini. One option is to rewrite it and start over again and think properly with a multi-threaded viewpoint. But this was not an option for us for two reasons. One, because we have a lot of customers that rely on us to have new versions every year, and we can't just go dark for 2 years as we rewrite things if we could do that in 2 years. The second is we believe internally that continuous integration and slow changes can transform any ball of mud code into another ball of mud code that's closer to what you want. And in particular, there's something really beautiful that happens when you face a problem and you say, I can't solve this. This is not possible with our architecture due to these problems. But you come back in a few years and it's trivial to solve. And it's not because you suddenly discovered a new way to solve the problem. It's because in those 2 years you became aware as a culture that the architecture was wrong in these ways, and you applied slow, continuous change and did some topiary to move your software in a direction where the architecture will be correct. And each stage of that process, you compile, you pass all the regression tests, and you have a working system. But at the end, you have something that's a lot more flexible or more directed in a useful technique. So our goal is to do that with multi-threading. One thing you do have to do, though, is clean up some of the old code. Thankfully, global variables have been out of fashion for a very long time. With code as old as ours, it dates back to when they weren't so hated. And so you need to try and find where are static variables used that will trip you up. Because these are things that are violently not thread safe, and you do not want to run into them one at a time. You want to try and preemptively find them. So one extreme solution I did was grep the actual symbol table of your library, looking for anything in the writable global address space and make sure that it's only stuff you know should be there. The Intel compiler has an option to warn about writing to statically allocated data, and you can put a macro to disable the warnings if it's something you know is safe. The other thing to watch out for is things like RAND and DRAND, which have implicit shared memory that will surprise you if you don't take it into mind. Then we have the question of where to start first. And as was said earlier, you have the choice of the task parallel world or the data parallel world, and you should start with the data parallel world. It's very common, and we've all probably been guilty of this. You write an algorithm, and you get some results for it, and you say, I've got this speed on a single core, and this algorithm is stupidly parallel, so it'll parallel perfectly. We should stop and think, if it's stupidly parallel it's stupidly easily to parallel, it's almost stupid not to make it parallel. So why are we not just making it parallel by default? And one answer was that slide earlier showing what you have to do to make a parallel algorithm with p-threads. It's a lot of work to set up, and you just freeze your brain and say, I'll just wait till this becomes a problem, then I'll make it parallel. So it's important to set up personally a workflow which makes it easy for you to write parallel algorithms when they're really easy to parallel, and also to convert the algorithms to parallel, because you might write it single-threaded to begin with because you aren't sure if it's going to be a data parallel, and when you're done you realize, oh, I could just make this parallel. There has to be an easy way for you to switch to that, and similarly to undo the process when you realize that it wasn't actually thread safe after all. Our first approach to making stupidly parallel stuff easy to do was to use that VEX language I mentioned earlier, because it works as a sort of kernel, so each particular element isn't allowed to see the data of any of the surrounding elements, and then this means that it's trivial to run all these processes in parallel, and so that's what we did. And the result is the more code we write in VEX rather than C++, the more stuff we get parallel for free. And so it's quite nice to be able to prototype stuff inside of Houdini and get an algorithm we like, and then realize we don't have to do anything more. We're actually done because it's fully multi-threaded and vectorized, and we're done with that. When you have stuff that is C++ code, there's two approaches, task versus thread-based. And as mentioned earlier, the task-based is the better way to go. We have a lot of thread-based stuff in Houdini because we started doing it before we knew about TBB. And the only real advantage of thread-based parallelism is if you don't have lambdas, it actually makes it a little bit easier to convert code 2 and 4. That's because that if you have an existing function you want to make parallel, usually there's some setup code you do before your inner loop. And with a thread-based model, you can just move all of that setup code into your callback functor and not worry too much about the overhead of it. Whereas in a task-based system, you'll want to marshal it and make sure it's only the inner loop that moves to the callback functor. When we do task-based parallelism, we use TBB, but we wrap it in our own macros to give us some control over it. In particular, we want to make sure that programmers who use it always specify a grain size. This is the size of those tasks. If you have 10 million numbers and you multiply them one at a time and have a task for each number, the overhead is going to completely crush your performance. And if you have 10 million per task, obviously you have no threading because you have only one task. And the good news is the actual performance shape is a bathtub, where you've got a very wide range where you can put this number in for the grain size. But it's very important you actually pick a number. The other thing we do is have UT serial for, which is a way to do a simple change word function to switch an algorithm from parallel to serial to see if the bug that we encountered is inside the parallelism or inside the algorithm. So over the years, we found a lot of things that went right or wrong. The first thing we learned was that if you have locks, they must always be reentrant. We actually, in the very early days, had, I think it was Windows was not reentrant and Linux was reentrant, and so it led to a lot of disasters. The reason for reentrant locks is you want to be able to reuse interfaces. If you have a mutex object and you have one interface on it that grabs the mutex and someone wants to factor code and reuse that interface elsewhere, you want them to be able to not have to worry about double locking, because factoring is something we want to encourage. However, you shouldn't lock in any case, and because if you're locking, you're not going to be multi-threading. Of course, if you are going to write to the same data address, you have to lock. So this doesn't say just don't have any locks. This says make sure your code does not require locks. And the reason why locks just don't multi-thread well is because all our mental models of how the synchronization occurs between the CPU are usually way too tightly coupled. We imagine like one clock cycle I release the lock, and the next clock cycle another CPU picks up the lock. At least that's what I imagined when I first did concurrency way back when. And you quickly become disabused of this notion. There's a massive cost to any lock where you lose your thread slice to someone else. And we're really against believing you know anything about what the CPU is. And this is because the architectures are always changing, and in our case particularly, we're a vendor, so we don't know what hardware you go and run our software on. So if we make assumptions about the hardware, it can prove tragically wrong on different systems. Without locks, we might consider the idea of switching over to atomics, where we can say that we're safe to read and write to the same address, provided we make it an atomic. And often you can convert your algorithm from a locked algorithm to one that just needs an atomic to share information. However, we have to remember these have to be synced across all the processors, and so they should be treated as uncached memory. In particular, it's important to be worried about cases where the atomics are hidden from you. Shared pointer is probably the best example of this, because it's a beautiful feature that's now in C++, but it does mean that if you have multiple threads that have the same copy value of a shared pointer, and they start copying it around by returning it by value everywhere, there has to be some atomic somewhere which is being synchronized. And this will show up in your profiles, and you'll realize that this is a very bad thing. The solution is to make sure you're careful about ownership, and don't just use shared pointer so you don't have to worry about ownership anymore. This is just a reiteration again that you do not want to just blindly fork into multi-threading. This is what always shows up when people start multi-threading algorithms. They take a test case of 10 million points, they multi-thread it, get it 10 times faster, and they're very happy. Then someone else has used that same function on 10 points, and they called it 1,000,000 times, and they're 100 times slower, and they're not happy. So no matter where you are, you should always ask, when should this be single-threaded instead of multi-threaded? Because there will usually be a data set where that's the case. It's incredibly important to keep your algorithms deterministic despite being multi-threaded. When you have a lock resolution, it's going to be resolved in an arbitrary fashion. And you need to ensure the result of your computation will be the same regardless of how those threads acquired the lock. Because if this doesn't happen, you can't debug normal non-multi-threaded bugs. Because you always have two types of bugs in your code, the multi-threaded bugs and the normal everyday bugs that show up in single threading. And you want to keep those separate, because the multi-threaded bugs are horrible to work with, and the single-threaded bugs, we already, they're not fun, but at least you can deterministically recover them. But if you blur them together, then you have a lot of trouble trying to debug things. A similar issue is trying to make sure you behave the same regardless of the number of threads in your system. We don't do this very well because we still have a lot of thread-based logic in our code, and also we drop back and run different code in single-threaded mode, which usually results in a divergence. We advocate that every host program should have command line control of how many threads it's going to use. This isn't a strict requirement. We'll have additional threads to do background I/O or network traffic, but this is sort of the number of live working 100% threads you expect to have. And this allows people, when they put your program out onto a render farm, to split machines up without having to use VMs. And it also allows you very easily to debug and do performance testing. You can find out if it's a multi-threading bug by just just running your program with a single thread. You don't have to recompile. And you can do performance tests to test scalability in a trivial fashion. When you build out your multi-threading, when you decide not to have any locks, it's tempting to duplicate data structures you're going right to in order to ensure you can write to them in a lock-free manner from different threads, and then afterwards maybe do a multi-threaded merge. The problem is you're going to end up with memory use which is proportional to the number of cores you have. And the number of cores that we saw earlier are going up and up and up. And even if you aren't on Xeon Phi, you can easily have a 4-socket 10-core machine with hyper-threading and then using 80 times the memory. Memory allocation is something that we don't want to have in our inner loop, but it will show up in your inner loop, and especially as you increase the amount of multi-threading you do. Amdahl's law means that eventually you're not just multi-threading the adding up of all of your points on your grid, you're also trying to multi-thread the allocation of all the polygons of your grid. And if you have any form of tree-like data structure, you find yourself doing a lot of allocation in parallel. And this is where TPP malloc is very fast, but we personally found it tended to fragment, so we advocate JE malloc as a good solution. So a very common problem is to have shared geometry cache, and we get this all the time in Houdini because we have these nodes that cook a piece of geometry, and other threads, maybe an external Python thread, may want to see the data of that geometry. And how can we ensure these readers and writers remain copacetic with each other? The traditional answer is a reader-writer lock. So if I want to write to the geometry, I grab a writer lock. If I want to read from it, I grab a reader lock, and we allow many readers but only allow one writer in. The problem is this is a test exam question in a concurrency course for a reason. It's very hard to get right, and I'm actually afraid to even try and use one because using it I'll probably mess it up. So let's just look at what a reader-writer lock would look like. So I've got my main thread and my Python thread, and I'm busy reading geometry in the Python thread, so the main thread has to block and wait for its chance to write, and then only when it's done writing is Python is allowed to pick up and continue. These two slides I'm going to claim are actually the same result. They're different results because in one Python reads the old geometry a second time rather than getting the new geometry. However, if there's no other synchronization going on, if you haven't enforced any synchronization other than the reader-writer lock, logistically it could have been the case that the Python thread ran faster and got all of its reading done before the main thread. So your whole system should support this and consider this a valid program execution model. So even if this is the time that occurs, we could return this result, and we need to remain consistent. And in particular, this result here is the same as writing to a copy. And so if we allow the many readers to just keep reading the original data until it's done, and now is write to a copy of the data from the main thread and post it when it's done, we can overlap all the computation. So this is what we tend to use, which is based on the idea of copy on write. And so for copy on write, the first thing you need to know is whether or not a function is going to actually modify your geometry, because you need to forbid those in the non-writer passes. And here we're very lucky that we used the Const keyword from early on in Houdini, and we thought it would give us performance improvements from the compilers, but it never did, but it did give us a nice compiler-enforced contract on the code. We found over many years that if people were in a hurry and not interested in worrying about const, they didn't cast it away, they just didn't put it in there in the first place. So all the const that showed up tended to be things put by people in a maintenance frame of mind that were being careful about putting it in there. So more so than function names or comments or parameter names, const is a keyword we learned we could actually trust to tell us something's going to be thread safe to read. The other feature we have is a lack of garbage collection. So because of this in C++, you always have an idea of ownership. And this helps you a lot when you want to serialize data, you know who owns it to write it. But it also means that you tend to have a low ownership count. So only one person owns something. So if you have a shared pointer for the cache, I'm not going to have multiple copies from my particular algorithm, I'm only going to have a single copy. So we can use those two together by minimizing the use of shared pointer to get at the idea that sole ownership is a writer lock. So if I'm the only person that owns a copy of a piece of data, I know that no one else can be reading it at the same time because they'd have to also own a copy. So in particular, I can make a write data and a read data function, and the read data just returns a raw pointer, so it doesn't gain additional ownership, and the write data makes unique first, so make sure that this particular instantiation is the only copy, and then it's safe to write to. This isn't a silver bullet. You have to keep this in mind when you're using it in the future. And first problem is excessive sharing. If you use shared pointers by value everywhere, you'll find that as you called your subthreads, each one gained ownership. And so each one unique their own copy and then threw it away when they were done, and so your original copy wasn't changed. But this is a reason why when you call the subthreads, you should have used raw pointers, because the subthreads do not require ownership. The ownership is being held by the parent thread, and so they should just get a raw float star. Similarly, you can get pointer aliasing as a serious problem, where if you read the value before you get a write lock on the data, you'd actually end up pointing to some data you don't own, and another thread might free it while you're reading. But this is actually an aliasing problem in general that you had here, so you needed to have sorted that out by making an actual copy of the foo array if you're going to read it. For the next part, I'm going to talk about a series of structures we've added to Houdini, two of which are our own, and one of which is just a wraparound TBB. And these, I don't have source code here because I don't want anyone trying to write it down and getting something wrong. But if you download Houdini, which you can get the apprentice version of, and go into the toolkit, include directories, there is a UT directory, and in there you can find UT task lock and UT task exclusive that show how we tried to do these. And if you find bugs with them, please let us know. Task locks are to solve a big problem that we ran into. We talked about at the beginning that locks need to always be reentrant, and we found that there's actually a meta level of reentrancy that's very important to have. So if we look at this sort of global cook lock, where we've got some data structure in Houdini that can't be written to by multiple threads, and we have a Python thread and a main thread trying to gain ownership, we can have a lock and they both take their turns right into it and things work. But when we started multi-threading, we could have the main thread call into Vex and generate, let's say, 4 subtasks, and they all run on separate threads. And then one of them decides it needs to do some more geometry cooking because it discovered a dependency or it needed to know the value of another node. And this is going to immediately block because it's on a different thread, so it can't be reentrant. But this is a valid thing to do because the main cook thread we don't have to worry about finishing until the Vex1 task is done, and that won't be done until Vex2 is done. So it's safe to have recalled into the cooking engine at this point. We can't release the lock on the cooking engine, however, because then that foreign Python thread might jump in and start deleting the node we're working on and produce bad results. So our solution is to have a tree of task owners. So there's a root task owner, and every time you have a subtask you call into, it has a task owner which points to that root. And we store this in a thread local storage, and every time we start up a task, we basically push this onto our current task owner list. And then when we have a task lock, what we can do is check to see if the current owner is our parent, or a parent. And if it is, we can replace the owner with ourselves, acquire the lock ourselves, and then replace the owner back to the parent when we're done. So in particular, we have this sort of flow where the TBB1 thread is able to acquire the lock because it's a child. The TBB2 thread is not allowed to acquire the lock because it's a sibling, and so it has to wait its turn. And so we have only a single threaded calling back to the cook library, but we haven't got a deadlock in place. This is a big result, however, in composability. And as mentioned earlier, this is when you have a threaded function call another threaded function, and it happens more and more as you spread out your threading. So you have cases which used to work just fine, and then someone decides to multi-thread something, and usually like, yay, good job, you multi-threaded the KD tree. But now Vex deadlocks. So why? So let's look into what happens when we have composability. I have 4 threads all try and build a KD tree of the same data at the same time, and one of them acquires the lock and starts working, and then it creates 4 subtasks because it was multi-threaded, and each of these runs in turn, and everything seems to work fine, and this seemed to be okay. It's sad that it's single-threaded, but at least it works. But then you run it on a system that's heavily loaded or otherwise in a strange state, and you have deadlocks or live locks or very strange behavior. And this is what we found happens. You get 3 threads picking up Vex3, and that 4th Vex4 thread, a task, just didn't bother to be picked up for whatever strange reason. These 3 then grab their KD tree building, and now all of a sudden it looks like we're ahead of the game. We have 2 threads cooking KD trees at the same time, but Vex4 suddenly gets stolen into TBB1. And This is a disaster because it's going to try and grab that KD tree lock. If it's a task lock I described earlier, it's a sibling, so it's not going to be allowed to re-enter it, and it's going to deadlock. In our particular implementation, we actually allow it to re-enter, but that doesn't save you because you can't unwind the stack back to finish the vex2 stuff because your vex4 function is sitting on the stack above you and can't finish until it gets the KD tree result. So task stealing does lead to these sort of deadlocks, and we have to remember that the stack itself has an implicit lock in it, which is going to show up with task exclusive. But first, I'd like to quickly mention the solution to this. There is in TBB something called a task arena, and this moved from the preview to the mainline in TBB 4.3. And reading the documentation talks a lot about controlling thread pools to make sure some threads don't starve other areas. However, we were very happy because it actually solved the lock-in problem, and we did this in Houdini 14, and touch wood, it's been working. And I hope it continues to work. The idea with the task arena is first we acquire a lock normally, and then we build just in time a task arena, and we execute our code inside that task arena. And when the thread gets assigned to a task arena, it doesn't allow any external tasks to be assigned to it. It only grabs tasks from that are generated from that subthread. And then when it completes, we can release our lock. So in particular, when we have this bad case, the KD tree is put in a task arena. Other worker threads are allowed to migrate in there if they wish. But that vex4 is forbidden from going into that task arena in TBB1 until the KD original task arena area finishes executing. And so this guarantees we don't have deadlocking. So some important things are if you make a lock-free algorithm, it might not be lock-free because you might have implicit stack lock. I've said this a few times because it's hard to understand and it does show up. I don't think you can reuse task arenas because their master thread gets assigned when they're first used. And so it's a very expensive thing to do. But as we mentioned earlier, locks are expensive in general, so you shouldn't be too surprised. And you have to make sure you catch exceptions. I thought 2 weeks ago I wasn't able to present this because I had a live lock in task arena, but it turned out to be I had an uncaught exception that was leaving the system in a very strange state. So do watch out for that if you see problems. So a structure we made is what we call task exclusive, and this is designed to solve the problem that we want to have multi-threaded execution. We don't want all those other threads just blocked there waiting. We want them to be able to do work as well. The idea is to post a task from all threads simultaneously, and that task's job is to enter a race to get the right to compute the resource. And one task will win this race and just compute the KD tree normally, and the other tasks will just recycle themselves and add a dependent task to that winning task succeeding. And so then the task scheduler will eventually unwind them when the original one is done. But they're back in the scheduler then, and they can pick up those subtasks from the winning task. So the way this is supposed to work is we have vex1 through vex4 running. All of them try and build a KD tree, and only our KD3 in this case wins the right to do the work. And the other ones recycle themselves and put their tasks back onto the task scheduler, but as dependents to our KD3. And then RKD3 can spawn a bunch of tasks that now can be run on all of our threads. And then when we're done, those RKD1 through 4 guys can be brought back to life and finish their execution. We can unwind the stack and we continue on happily. This seemed to work great until, of course, again, we ended up with a live lock where the system was just sitting idle and looking for more work, but hadn't finished the work it was given. The problem is, again, you need a task arena to make sure that the stack can always empty back up to that recycled task. And this is very close to, again, you can see vex4. We just could get rid of vex4 and maybe solve all of our problems. But vex4 is sitting there, and it decided to run after that recycled task. And because of that, there's no way to unwind the stack now to get ourselves back to our safe state. And I'm going to just end here with a picture of what you get when you do info threads in GDP. This is with a 12-thread machine, so I've got 17 threads I'm trying to look through, and it's not fun to do back traces on all of them and look at big, long lists like this, where you're like, why is this not working? It's just sitting in the scheduler, waiting for work, but it's not done yet. And eventually you look in and you say, oh, wait a second, why are there 2 calls to task exclusive here? How did it manage to call itself twice? And you realize that you have basically a stack lock in place. So task arenas are a very useful tool for that. So I'd like to just conclude my section here by pointing out that it's very important to get a workflow yourself personally or in your institution. It makes it easy to parallelize things, so it becomes a habit and becomes something that isn't, something you have to think about doing. And also, however, make it easy to always switch back to serial for debugging and for performance testing and all those issues. JEmalloc, or a memory manager, I can't stress enough how important it is to use this, because as you start increasing your parallelism, eventually you'll hit the stuff that does lots of memory allocation. And I also do not believe you need to fully rewrite your code, but there's always the potential of continuous improvement to get there. So thank you very much. So I think we're scheduled for a break from 8 minutes ago until 10:30? No, it starts at 10:30. Oh, okay. All right. I thought we had till 10:15. Okay, I could have gone slower then. All right. Does anyone have any questions then? Excellent.
Morning. I had, on the memory allocation, I had a question. I believe I'm thinking about years ago, we ran into a problem with when we were using TBB's memory allocator, and we ran into a little bit of a snafu where a lot of allocation had been done on different threads, but then when it came time to delete, it was done on a different thread than where it was allocated, and that actually, the delete would cause a large hang because it was trying to synchronize. Mm-hmm. And just off the top, I hadn't heard about JEmalloc, and I was wondering how much of that right there improves that, and just generally wanted to point out that there are snafus that you can run into with trying to improve your memory allocation.
Yeah, our memory allocation scheme is very bad in that sense, insofar as we happily allocate all on one thread and then delete on different threads all the time. And so that's one reason why I think we like JEmalloc, and I think the TBB scalable malloc does a lot more, where it returns it to separate thread pools, right. But then you end up with that fragmentation problem because it can't ever clean it up. So JEmalloc was done to try and solve all the problems of memory allocation, not just the threading ones. And so it also works very hard on the fragmentation issues. So it's a bit slower and less scalable, but it definitely, I've had very few snafus like that with it.
Okay. And then I remember reading a while back in the TBB documentation, it recommended if you're doing anything that's blocking a lot, like doing I/O, don't use TBB, go use something else.
That's correct. I use pthreads for I/O. And so if I want a background thread just to save stuff in the background, I start up a normal pthread, and it sits there and blocks. And traditionally, you got some queue in between the two. I mean, TBB is great for that task parallelism type stuff, but you don't want to be blocking inside the tasks.
Cool.
Yeah, and TBB added something called TBB threads that to try to address the question you're saying, because if TBB is running on an 8-core machine, 8 task queues, if one of them blocks for I/O, it sits idle. So the concept of oversubscribing, which is what pulling up a pthread would do, TBB added something called TBB threads to let you explicitly say, hey, I want to have a task that oversubscribes the machines. You get the same effect if you go pull up a pthread and oversubscribe it. Either one is valid.
Yeah, that's how we ended up with like 17 threads on a 12-thread machine.
I've done worse.
I have a question on Houdini, since it's a very visual and there's a lot of user interface going on in there. Have you been able to leverage the tasks for any UI processing too? Since
no, we've not been successful with UI threading. We really, that's something we really want to do, but we've been focusing on just the massive data parallelization.
All right, thank you.
Mark from Disney Animation. We ran into an issue with thread local storage and task stealing, where if a thread was doing something and put something in local storage, and then some other thread came in or some other task came in and used that same thread and same local storage. This was with TBB and that. What solutions in that have you found for that kind of issue?
Oh, that's a very good problem, and actually, I think we've been lucky enough not to run into that problem, because we usually don't rely on the task storage. I guess the whole problem there is, yeah, I think we've just been lucky. So thank you for pointing that out. So to explain the problem, you have a thread that is calling into the TBB system, but it wrote something into local thread local cache, and you normally expect your children to all be the children you explicitly called, but it could suddenly bring in a whole sibling thread that also writes into that cache. I think, again, Task Arena would be an answer to prevent that, but it's a pretty heavyweight answer. So maybe you'd be better off having a thread ID storage that you use to store where you store that cache, or provide that write cache down to the tasks. Because again, thread local storage, I think, might be told to us that it's thinking of threads and not tasks, and so we should be doing like a reduced type task where you've got a place to write to that's given to you, rather than a magical place you get from the processor.
Right. Thanks.
Okay. If there are no more questions, we're going to be picking up again with Erwin talking about Bullet and OpenCL at 10:45.